Successful software systems grow, and so do their automated test suites. Many of the teams we work with have thousands or tens of thousands of automated test cases. Executing all of them takes weeks or sometimes even months. This is very slow from a feedback perspective. If I, as a developer, break something, it's painful to have to wait a week or a month to learn about this. In this presentation, I want to talk about how we can get fast feedback, even if running all tests takes too long. To get it out of the way, an obvious approach to get faster feedback would be to execute tests in parallel. However, this is often not possible. For example, in embedded systems, we often see test cases that are executed on hardware-in-the-loop test benches, like this one in the picture. Since they are very expensive, it's often not feasible to parallelize that. This is not limited to embedded systems, however. For business information systems, for example, we often see test environments that are difficult to replicate for other reasons, for example, because databases or other systems the tests interact with are hard to parallelize. So if executing all tests takes too long and we can't parallelize, what we're left with is choosing a subset of the tests that run reasonably fast. The trick is to select the subset in such a way that it finds most of the bugs in a very short time. And the basic idea behind test impact analysis, which I want to present first, is to select those test cases that run through code that changed since the last test execution. And I want to show why this works well with an example from our own code base. And I want to use a so-called tree map to visualize this. This is a tree map. A tree map uses rectangles to visualize components of software. And the size of the rectangle corresponds to the size of the component and lines of code. In this case, every rectangle is a package of our software. Now let's drill in. Now every rectangle is a file. And if we drill in even further, every rectangle represents a method in this code base. It still holds the size of the rectangle corresponds to the size of the method in lines of code. And now I want to use this visualization to show test coverage and changes. This is the code that changed for one ticket we implemented. Gray means unchanged, orange means new code, red means modified code. So this ticket that one of my colleagues implemented modified this bunch of methods here. Now let us execute our test suite on these changes. For this, I have a time-lapse video, which I start now. In the video, we execute 30 test cases per second. All the methods that a single test case executes are depicted in white, and then they gradually fade to green. You see that there are some areas where there's a lot of test execution. You see there's some areas where fewer tests execute through. But the most important thing I want to show with this video is that everything that was ever tested gets covered in green. However, our changes are still depicted in orange and red. I stop the video now. Since the changes are still covered in orange and red, even though we executed many hundreds of test cases, it shows that none of these test cases executed those changes. And this shouldn't actually surprise us, because back then when we wrote those tests years ago, we didn't anticipate those changes and write tests for them. However, if a test doesn't execute changed code, one cannot find a bug in that changed code. So from a test optimization perspective, there's a lot of potential in skipping those useless tests to speed up bug finding of the test cases that actually do execute changed code. And that's what test impact analysis does. Test impact analysis works in two steps. In the first step, we remove all those test cases that are not impacted by changes. In other words, we only execute those test cases that run through code that was added or modified. This shortens the list of tests. If we are lucky, this list of impacted tests is short enough and fast enough that we can provide really fast feedback. However, in practice, especially in systems with end-to-end tests, it's often the case that there are some code areas through which many or even all of the test cases run. And if we modify these code areas, then the selection step will still select very many or even all test cases. So we need a second step to get a speed up in these cases. And for this, we prioritize tests in such a way to make it likely to find new bugs quickly. Imagine we ran those test cases. Then some would pass and some would fail. Failure is depicted by the white cross on red background here. If we could, in an ideal world, order them in this way, then we would have all failing test cases at first. Then with the first failure, we could notify development that there's still a bug in the code base and stop all subsequent jobs in our pipeline. Now, we obviously can't order them this way, because if we could, we wouldn't need to run them. But what we can do is use heuristics that approximate this order of test cases. And there's a large body of research that investigates very many different test prioritization techniques. And we've implemented many of them. And the one that works best for us is this. We always choose that test case next that per second of test execution executes the most changed and not yet covered lines of code. And then we get a result like this, where we, with a very high likelihood, have failing test cases early. So if there's a bug in the code base, the selected tests will very likely find that very quickly. Now, how well does this work? To find out about that, you need a lot of bugs. And we did a lot of empirical studies where we got the bugs in two different ways. The first way is we looked at historical test failures from open source software systems, where we looked into the version history to see where developers committed the bug that caused the test case to fail, and then we would execute the test suite on the version that contains the bug and see if the impacted tests find that bug and how quickly they find it. The advantage of that approach is that it's realistic bug data from real-world software. The disadvantage is that you need very many open source projects with very many revisions to find not so many bugs, because typically developers don't commit the bugs that the automated tests can find. So we used a complementary approach where we introduce synthetic bugs using mutation testing. The advantage of that approach is that you can introduce thousands of bugs and know where they are beforehand, and then also run the test cases and see how quickly the test impact analysis finds the bugs. The disadvantage is that they are not as representative for real-world software because they are made-up bugs. But in combination, and because both approaches showed the same picture, we get a very reliable result. And in our studies, we learned that we find 80% of the bugs in 1% of the time it takes to execute the entire test suite, and 90% of the bugs in 2% of the time that it takes to execute the entire test suite. Now, 100% bugs here means all the bugs that the entire test suite can find, not all the bugs contained in the software system, because we don't know where the bugs are that we don't know about. But we get a very, very big speed up here. And this is for two reasons. The first reason is that test impact analysis is a very efficient approach, but also because retest all is a very inefficient approach for continuous testing. However, this approach requires a lot of effort because we need not only capture test case specific coverage, but we need to integrate into continuous integration. And every single time a test run is started, we need to measure which code changed and then on the fly select the impacted test cases. So what we spent the last years working on is to see if there's a simpler way for the teams that don't want to invest this effort. And we found one approach which we call Perita Optimization, with the goal of finding 80% of the bugs in 20% of the time. And I want to outline how this works. And the basic idea behind Perita optimization is that we want to find many bugs in a small amount of time, even though we do not know what changed since the last test run. And the basic idea behind that is this. If we have a test suite, then often a single bug does not cause a single test case to fail, but a single bug might cause many test cases to fail, and there can be several bugs at once in the software system. In this example here, we have the orange bug that causes 2 test cases to fail, we have the blue bug that causes 4 test cases to fail, and we have the purple bug that causes 1 test case to fail. And the important idea is to know about the bug and to help a developer fix it. It's enough to have a single test case that fails and reveals that bug. We don't need every single failing test case. So if we manage to select a subset of the tests that finds many of the bugs without all the failing test cases for a bug, that's still enough to help developers fix those bugs quickly. And this is possible because in many historically grown test suites, there's a lot of redundancy between very similar test cases. And empirically, we know that those similar test cases often fail together when they reveal a bug or don't fail at all. So in many cases, it's sufficient to select a single test case from this cluster of similar test cases if we want to find new bugs quickly. I also want to demonstrate this using an example. And for this example, I use a software system called Pixelito, which is a bitmap paint program. This is a screenshot of it. It's an open source Java software. And this is the tree map visualization of its code packages, of its files, and of its methods. And now I want to use this visualization to visualize test case specific coverage of Pixelito to show what I mean with redundancy between test case executions. Because what we did was measure the test coverage of the manual test cases for Pixelito. And we did that for the entire test suite. And the key thing I want to bring across now is that the sequence of test execution impacts very strongly how quickly we cover big parts of the system. In the Pixelito test suite, the first test case that gets executed when we execute the tests in the default order is called test Gaussian blur. And this is the method it executes. And now, since this is the first case we execute in the test suite, every single method it covers is new coverage, and we depict it in green. The second test case in the test suite is called test motion blur. And in this tree map, you see all the coverage it has in green and blue. The new methods it covered that were not covered by a previous test case, in this case Gaussian blur, are depicted in green, and the methods that were already covered are depicted in blue. And because it's also a blur, it tests a lot of code that was already tested by the previous blur test. The third test in the suite is called test lens blur. It has less green, and the fourth test is test smart blur, hardly any green at all. It tests mostly code that was tested already. Now, if I depict this on one slide, you see in the little bars here to the right-hand side of the tree maps how the green gets less and less, so every test we execute adds less and less new coverage, or in other words, less and less likelihood of finding new bugs per test execution time. However, we can use this test case specific coverage to optimize the order of test cases in such a way that we always select that test case next, that per second of test execution adds the most not yet executed lines of code. And if we do that, we first select test create and modify selection. The second test we select is test change view settings. and it also sounds very different. So it probably does something very different than the previous test. And you see, I mean, it does cover some blue code that was tested already, but there's still a lot of green code here. The third one is test second layer, still a very different name. And test save image, again, a very different name. And if we plot this the same way, and just let me move to the side, you see that there's just a lot more green code in the bars here, which means a lot of edit code coverage that is much quicker in testing that application than the default sequence. Let's plot this in a diagram. On the right-hand side, we have the relative runtime. 100% means the time it takes to execute the entire test suite. And on the y-axis, we have the relative coverage. 100% means the coverage of the entire test suite. In blue, you see the default sequence, where we test the entire blur cluster. And in green, you see the optimized sequence. And if we cut off this diagram here, which means we only select a subset of the test for execution, you see that in our optimized setting, we execute way more code than in our default setting. Now, this was a toy example of Pixelito. We've done this in a lot of open source projects, the same way we did with test impact analysis, both with the real-world historic bugs and also with synthetic bugs we introduced through mutation testing. And in our experiments, we found that it takes us 6% of the execution time on average to find 80% of the bugs, and 11% of the execution time to find 90% of the bugs. So if we compare that with test impact analysis, it's not as good. For test impact analysis, we had 1% of the time for 80% of the bugs and 2% of the time for 90% of the bugs. However, it's still a very significant speed up, and it requires much less effort. So let's compare that. Test impact analysis selects tests with respect to the code changes we did. We find 90% of the bugs in 2% of the time, but it requires continuous recording of coverage and tight integration into your test automation framework and the continuous integration. Perita Optimization selects tests independent of code changes by exploiting redundancy between test cases. It takes us 11% of the time to find 90% of the bugs, but it's sufficient to record test case specific coverage every now and then, for example, once per quarter. And in our experience, both approaches are valid depending on how much effort it is to integrate into your setting and how big the pain is because of slow test execution. Now, how can you use this for the robot framework? In the first step, we need to, independent of which approach we use, in the first step, we need to record the test case specific coverage. For that, you run your tests and you use a coverage profiler to record the test case specific coverage. We have created a plugin into the robot framework, which is available as open source under the URL given on the slide. And we have also open sourced our coverage profiler for Java, which is an adaptation of the Jacoco open source profiler. So these two work together to record test case specific coverage for Java tests for the robot framework. This command line to execute your tests. And then the test case specific code coverage gets written to the hard disk, and you can use it with any tool that uses code coverage, including TeamScale, our own tool that we use for the Perita Optimization and the test impact analysis. In the second step, we need to integrate this into CI to get the speed up. If we want to do Perita Optimization, we upload the test case specific coverage, run Perita Optimization once, and then export the static list of Perita tests, which we can then integrate into the continuous integration. This is a single shot thing because it's a static list, independent of the changes. If we want to do a test impact analysis, we need to integrate team scale into the continuous integration, so that on every single test run, team scale pulls the changes from version control, computes which methods were affected, and then on the fly selects and sorts those tests that can find new bugs most quickly. This is more effort for integration, but also gives a bigger speed up. Now, the Jacoco agent and the robot plugin are open source. TeamScale is not, because our business model is to sell our software. So what you can do with the open source part is capture test case specific coverage and write it down and use it with other tools. And you can also use the free version of TeamScale for the Perita Optimization, but you need the commercial one for the test impact analysis. And it feels a bit weird to say this, to talk about closed source software in an open source conference, but this is our business model, and this is us and the families that live from the license revenue. So I hope you bear with us here. Thanks a lot for the time. I'm open for questions, and I'm very much looking forward to discussions.